So far we've looked at case 1 for the chain rule, and that was where our composition ultimately created a real valued function of one variable, so that the derivative that we were calculating was a full derivative. Case 2 is going to be where we're creating a real valued function of multiple variables, so that we'll be creating a partial derivative. Okay. So if we have z as a function of x and y, and of course this would generalize if w was a function of x, y, and z, and then x and y are both themselves functions of two variables u and v. Now I've written that as the individual functions. X is a function of two variables and so is y. If I wanted to, I could view that as one function. It would be a vector valued function of two variables. So the input is two-dimensional, it's a point uv. The output is two-dimensional. It's going to be a point xy, where x and y are both functions of u and v. Almost all of the functions that we work with this semester are going to have either their input or their output being just one-dimensional. We will occasionally, though, see functions like this. So I could interpret this as one function if I wanted to, although because this is not what we're generally studying, the book has chosen to just write it as the individual component functions. Okay, so how would this work? Well, I'm going to create a diagram that gives me the dependence relationships. So z is the ultimate output, that goes on the top. It's a function of x and y. But x and y are then both functions of u and v. Now, this diagram explains why I like to write these variables twice. This u is exactly the same as that u. But take a look at what happens if I try to just write u and v once. Then x depends on u and v, and y depends on u and v, and the lines start to get crossed and the diagram starts to get messy. So that's why it's my preference to always just say x is a function of these variables u and v, and y is a function of these variables u and v, and leave it to my common sense to recognize that u and u are not two different things. That's the same thing, just occurring twice. Okay, then when I have this, just like with our previous diagram, every line gives me a dependence relationship here. Okay. So I can say, z is a function of two variables, so these lines are going to correspond to partial derivatives. So I'd have the partial of z with respect to x, and the partial of z with respect to y. And again, if I wanted to call that the partial of f with respect to x and y, I certainly could. Okay. Now here, x is also a function of two variables. So these are going to be partials. Partial x, partial u, partial x, partial v. Okay. Now here I do need to call that just partial of x with respect to u. I couldn't use the name r here because r isn't just giving me x. R is giving me both x and y. Okay, here this would be the partial of y with respect to u and the partial of y with respect to v. So every derivative on my table here is a partial derivative. Now, z ultimately depends on these variables, u and v. So z is going to have two partial derivatives that I could calculate, partial of z with respect to u, and then the partial of z with respect, let me give myself some more space here, partial of z with respect to u, and the partial of z with respect to v. And all I do, if I'm concerned with the partial of z with respect to u, I'm only going to be concerned with the paths that connect z to u. So that would be this path and this path. Okay. Because of course, when I'm taking a partial with respect to u, I'm going to be holding v constant, so that's not affecting the change in z. Okay. So along each path, I multiply together those partial derivatives, and then I simply add the results. So this would be the partial of z with respect to x times the partial of x with respect to u. That's the product of the partials along that path, plus the partial of z with respect to y times the partial of y with respect to u. That's the product of the partial derivatives along that path. And then, of course, if I wanted to calculate the partial of z with respect to v, now I no longer care about the paths that connect z to u. Now I would care about these paths that are connecting z to v. Okay, so we would get the partial of z with respect to x times the partial of x with respect to v, plus the partial of z with respect to y times the partial of y with respect to v. And of course, in practice then, these partials here would originally have x and y's in them. Just like in the previous case, the rule is in our final answer, we should only have the variables that occur on the bottom level here. So we should be able to write everything in terms of u and v. So let's just try an example. And what I'm going to do is, rather than use u and v, I'm going to use r and theta. Because sometimes I do want to switch from describing things in my rectangular coordinates x and y to describing them in polar coordinates r and theta. So let's say that we've got z is equal to f of xy. Let's go with e to the x squared y. Okay. And then we would have x, of course, is just r cosine theta, and y is r sine theta. Those are my usual formulas for expressing x and y in terms of polar coordinates. So now here's my diagram. Z is a function of x and y, each of which is a function of r and theta. So if I wanted to calculate the partial of z with respect to r, now that's going to be a partial derivative because z is ultimately depending on more than one variable. It's depending on both r and theta. Now if I'm doing that, I'm taking a look at the paths that connect z to r. So that would be this path and this path. So this is the partial of z with respect to x, and this gives me, actually let me do this in purple. This is the partial of z with respect to x, and this would be the partial of x with respect to r. This would be the partial of z with respect to y, and this would be the partial of y with respect to r. Notice, if I'm just calculating this, we're actually going to go back and calculate the other one, but if I'm just calculating this, I don't have to fill out the entire table. If I only want the partial with respect to r, I really don't care about what's going on with theta. Okay. All right. So this would be the product of these derivatives. So partial z, partial x, partial r, plus that would be the product of these partials. Partial z, partial y, partial r. And now I can go ahead and calculate what those are. Notationally, some of you might choose to write out these derivatives individually off to the side before you go and plug in. That's totally acceptable. I would encourage you to write out the formula like so and then plug in, whether you're calculating at the same time as you're plugging in or whether you've individually first calculated all of the related partials. Okay, I'm going to just go ahead and calculate as I plug in. So partial z with respect to x, I'm going to get e to the x squared y times the partial with respect to x of that exponent, that's going to be 2xy, which I'm going to write up front. Partial of x with respect to r, that's just going to be cosine of theta, because theta and any function of theta are constant with respect to r. Plus partial of z with respect to y, let's see, that's going to be my e to the x squared y times the partial of x squared y with respect to y is just x squared. And then partial of y with respect to r is sine of theta. Okay, and of course this is an intermediate step because I've got all my variables here. I did not want to have a function of 4 variables. I was trying to switch to just the 2 variables r and theta. So now I'm going to go through and all of the x's become an r cosine theta and all of the y's become an r sine theta. I think it's actually going to be a little bit easier if I give myself some more space. So we have 2xy e to the x squared y cosine theta plus x squared e to the x squared y sine theta. And I'll just remind myself that x is r cosine theta and y is r sine theta. Okay. So now we can plug in. So I'm going to have 2. X is r cosine theta, y is r sine theta. I'm just going to consolidate those r's. So I'm going to write that as r squared cosine theta sine theta. 1 factor of r from the x and 1 factor of r from the y. Times e to the x squared times y. That was all up there in the exponent position. That's going to give me an r cubed cosine squared theta sine theta times a cosine theta. Now I already had a cosine theta there, so I'm just going to modify that and make that a cosine squared theta. Plus my next term, x squared is going to be r squared cosine squared theta. E to the x squared y, we just saw that that was going to be e to the r cubed cosine squared theta sine theta. And then times a sine theta. I left a little bit of space there so that I could write that in front. The order in which you write things does not matter, but I find it helpful when I've got an exponential expression to try to not write stuff after that so that if my handwriting gets a little bit sloppy and this exponent accidentally drops down, I don't suddenly think that this stuff was part of the exponent. Okay, excellent. So that gives us our formula for the partial of z with respect to r. Okay. And here, I could not say that that's the partial of f with respect to r, because f only refers to this part of the diagram. Okay. That's z, doesn't matter. Now I'm viewing z as a function of r and theta, but f wasn't a function of r of theta. What I'm looking at is a function composition. F was a function of x and y, each of which was in turn a function of r and theta. Okay, let's go ahead and calculate the partial with respect to theta. So that was partial. So now I'm concerned with the paths that connect z to theta. So they start the same. They start with the partials of z with respect to x and y, but now I'm going to be concerned with the partial of x with respect to theta and the partial of y with respect to theta. Okay, so the partial of z with respect to theta is partial z partial x, partial theta. That's the product of the partials along that path, plus partial z partial y, partial theta. Partial z partial y, partial theta, that's the product along this path. Okay, so the partial of z with respect to x, we did that a moment ago. We said that was going to be 2xy e to the x squared y. Partial of x with respect to theta is going to be a negative r sine theta. Do just be careful that that's multiplying by a negative. Don't omit those parentheses because then it looks like a subtraction problem. Plus, partial of z with respect to y was x squared e to the x squared y. Partial of y with respect to theta is just r cosine theta. And then again, I want to get everything in terms of just r's and thetas. Okay. So we said 2xy, that was 2r squared cosine theta sine theta. E to the x squared y was e to the r cubed cosine squared theta sine theta. And now we're multiplying that by a negative r sine theta. I'm just going to bump that negative sign to the beginning. Another factor of r is going to make that, instead of r squared, that'll be r cubed. And another factor of sine will make that a sine squared theta. Plus, x squared is r squared cosine squared theta. E to the x squared y was e to the r cubed cosine squared theta sine theta. And then I've got another factor of r. So again, I'm just going to change that from r squared to r cubed. And I've got another factor of cosine theta, so I'm going to change that from a cosine squared to a cosine cubed. So that ultimately we have this just in terms of r and theta.